Strategy in finding indefinite integrals. First, rewrite the integrand. Use strategies such as applying properties of exponents, radicals, and fractions, factoring and dividing out common factors, distribution of a factor by multiplication or division, and multiplying and dividing polynomials. For transcendental functions, use special identities to express the integrand as an equivalent form that is easier to integrate. Second, integrate the integrand with respect to the variable of integration. Apply integration rules such as sum or difference rule to transform a complicated integral into simpler integrals. Then, apply basic integration rules to complete the integration process. In addition, apply other integration rules that involve transcendental functions when necessary. For composite functions that are not covered by basic integration rules, apply the substitution rule, which will be discussed in more detail in a future presentation. Meanwhile, integration by parts is an advanced integration technique that splits a complicated integrand into a product and a simpler integrand. This technique will be discussed in a future presentation. Third, simplify the indefinite integral. Use properties of exponents, radicals, and fractions to rewrite and/or simplify the indefinite integral. The indefinite integral may also be simplified by factoring, dividing out common factors, and simplifying or combining rational expressions. Fourth, verify the indefinite integral by differentiation. The result of differentiating the indefinite integral must lead to the integrand or its equivalent. First, rewrite the integrand such that it fits an integration rule. Applying properties of exponents, radicals, and fractions. Use these properties to rewrite an integrand so that it fits an integration rule. Examples: subtract exponents for quotient of the same base, while add exponents for products of the same base. A radical can be decomposed into a product of radicals. Note that splitting a radical is only applicable to products and quotients of factors. A complex rational expression can be reduced into a simpler rational expression by flipping the denominator and multiplying the result with the numerator. Factoring and dividing out. Example: if possible, factor the numerator and denominator completely, and then divide out the common factors between the numerator and the denominator. Distribution: multiplication and division involving a polynomial and a monomial. Decompose a complicated product or quotient into a sum of terms. Examples: multiplication. Distribute the monomial by multiplying it with each term of the polynomial. Division. Distribute the monomial by dividing each term of the polynomial by this monomial. Multiplying and dividing polynomials. Involve two polynomials. Examples: multiplication. Multiply two polynomials by multiplying each term of the first polynomial to every term of the second polynomial. Then, get the sum of all these products. Division. If the degree of the numerator is greater than or equal to the degree of the denominator, divide the two polynomials by performing long division method. Multiplication and division of polynomials can be tedious operations. Consequently, an advanced technique such as substitution rule can be implemented directly. Second, integrate using integration rules as a guide. Sum or difference rule. Apply the sum or difference rule to sum or difference of terms. The integral can be distributed over addition or subtraction. Product and quotient. There are no product and quotient rules in integration. However, if the integrand is a complicated product or quotient, try to express it as a sum or difference of terms, and then integrate each term following the sum or difference rule. There are also other methods to integrate products and quotients such as, substitution rule, which is useful for composite functions, and integration by parts, which is applicable when the integrand is composed of a factor that is easy to integrate and another factor that has a simpler derivative than the original integrand. These techniques will be the topics of future discussions. Basic integrals. After rewriting the integrand into manageable terms, apply basic integration rules to complete the integration process. Constant rule. Power rule. Constant multiple rule. Reciprocal rule. Absolute value rule. In addition, apply other integration rules that involve transcendental functions when necessary. Exponential functions. Logarithmic functions. Trigonometric functions. Inverse trigonometric functions. Hyperbolic functions. Inverse hyperbolic functions. Composite functions. Substitution rule. For a composite function, apply the substitution rule of integration. In general, the integral of a composite function multiplied by the differential of the inner function is equal to the integral of the outer function with respect to a new variable substituted for the inner function multiplied by the differential of that function. The following examples show when to apply a basic integration rule and the corresponding substitution rule. The power rule for a variable x raised to a real number n. Is x raised to n plus 1 all over n plus 1, plus c. Example: the integral of x squared dx is equal to 1/3 of x cubed, then plus c. Meanwhile, the general power rule for a function raised to n multiplied by the differential of that function is equal to that function raised to n plus 1 all over n plus 1, then plus c. Example: the integral of 3 times the square of quantity 3x minus 1 dx. Where u is equal to 3x minus 1, and du equals 3 dx, is equal to 1/3 of the cube of quantity 3x minus 1 plus c. Third, simplify the integral. The following are some of the guidelines that can be applied to simplify the integral. Factoring out a common factor. Examples: factor out the variable with lowest exponent. Subtract this exponent from the exponent of the same variable of each term. This is the equivalent of dividing each term by the common factor. Simplify the result. Aside from factoring the variable with lowest exponent, the constant multiplier with lowest magnitude can also be factored out. Divide each term by the product of the constant multiplier and the variable to be factored out. This is the equivalent of dividing each term by the product of the constant multiplier and the variable to be factored out. Simplify the result. Simplifying rational expressions. Example: a rational expression can also be simplified by combining multiple rational expressions into a single rational expression using the least common denominator method. To verify if the combined rational expression is correct, divide each term of the numerator by the least common denominator. It should return the rational expressions. Combine like terms. Fourth, verify the answer by differentiation. The indefinite integral is correct if the result of its differentiation leads back to the original integrand or an equivalent form of the integrand. Examples: find the indefinite integral. Number 1. The integral of the product of quantity x minus 6 and quantity x plus 3 all over x raised to 5 dx. Solution. First, rewrite the integrand. Transform the integrand into a sum or difference of terms so that the sum or difference rule can be applied. Multiply the two factors in the numerator. Divide each term in the numerator by the denominator. Apply a property of exponents. Integrate the rewritten form of the integral and then simplify. Integrate using basic integration rules. Simply using a property of exponents. Simplify using a property of exponents. Combine the rational expressions. Check if the combined form returns to the original sum or difference by dividing each term of the numerator by the denominator. Therefore, the integral of the product of quantity x minus 6 and quantity x plus 3 all over x raised to 5 dx is equal to the negative of quantity x squared minus 2x minus 9 all over 2x raised to 4 plus c. Finally, verify the indefinite integral by differentiation. The derivative must be the same as the given integrand or its equivalent form. Number 2. The integral of the quotient of quantity cosecant squared of x minus 1 and quantity 1 minus the cosine squared of x all raised to 1/2 dx. Solution. First, rewrite the integrand. Use trigonometric identities. A quantity raised to 1/2 is the same as the square root of that quantity. The square root of the square of a quantity equals the absolute value of that quantity. Use another trigonometric identity. Integrate and simplify. The integrand contains the absolute value of a quantity. Note that the absolute value of a quantity is defined as follows. Consequently, the integral has two cases. First, the integral of the cosecant of x times the cotangent of x dx. If the cosecant of x times the cotangent of x is greater than or equal to 0. Second, the negative of the integral of the cosecant of x times the cotangent of x dx. If the cosecant of x times the cotangent of x is less than 0. Integrate using a trigonometric function rule. Because the two cases differ only by the sign, the integral becomes the negative cosecant of x times the quotient of the cosecant of x times the cotangent of x and the absolute value of the cosecant of x times the cotangent of x plus c. This quantity determines the sign of the indefinite integral. It is equal to 1, if the cosecant of x times the cotangent of x is greater than or equal to 0, or it is equal to -1, if the cosecant of x times the cotangent of x is less than 0. Finally, verify the indefinite integral by differentiation. The derivative has two cases because the quotient factor is either +1 or -1. The derivative is the absolute value of the product of the cosecant of x and the cotangent of x, which is equivalent to the given integrand. Number 3. The integral of quantity 2x plus 7 multiplied by the square of quantity x squared plus 7x plus 12 dx. Solution. Rewrite the integrand and integrate. The integrand is composed of a function of x raised to the power of 2 and the differential of that function. Let u equals x square plus 7x plus 12 and du equals 2x plus 7 dx. Integrate using the power rule. Substitute u equals x squared plus 7x plus 12. Thus, the integral of quantity 2x plus 7 multiplied by the square of quantity x squared plus 7x plus 12 dx is equal to 1/3 of the cube of quantity x squared plus 7x plus 12 plus c. The technique used here is called the substitute rule of integration, which will be discussed in another video. This method of finding the indefinite integral is faster than expanding the square of the polynomial and multiplying it with the binomial before integrating. Verify the indefinite integral by chain rule of differentiation. Because the indefinite integral is a composite function, use the chain rule of differentiation to get the derivative. The derivative must be the same as the given integrand. Or its equivalent form. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.